Thanks a lot for the organizers for inviting me. So this talk is going to be about an approach to information theory, which is a bit different from the usual approach, in which in information theory we look at an information processing task, at an operational task, and we try to relate the optimal rates to entropic quantities. Okay, so here I'm going to try to take a little bit of a different approach, where I'm going to look at this as an optimization problem, and I'm going to try to find what are the best algorithms we can get in order to achieve this task in an optimal way. Okay, so yeah, so so this will be based on the joint work, a little bit old joint work with Sid Barman, which is about the classical case, so the classical channel coding picture, in which we have, I think, very nice results that basically, I mean, that are tight. And also then I'm going to talk about more ongoing work with Mario and other people on the quantum case, but you'll see that this is much less well understood. Okay, so let's start. So the basic problem I'll be concerned in with this talk, throughout this talk, is I have a noisy channel. So I have some model of noise, and I would like to reliably communicate using this noisy channel. Okay, so as I said, I'll start with the classical case. So now I have a classical noisy channel. So everything will be finite dimensional here. So the way a noisy channel is defined is as follows: is I have a finite set of inputs, so which I'll call x, okay, and a finite set of outputs, which I call y, and this w of y given x is just going to be the probability that I see the output y if the input was x. Okay, and my task is going to be to try to communicate some message. Okay, so the message set is going to be the integers from 1 to k. Okay, so I want to send k different messages. I'm going to label it by I. Okay, from Alice to Bob, using as a resource this noisy channel. Okay, so and our task as a system designer is to design a system that will allow us to do that in the best possible way. Okay, so let's formalize this a bit more mathematically. So what I would like to construct is two things. First, an encoding function, okay, so which takes a message and outputs something which lives in the inputs of this noisy channel, okay, so which I called x, remember, and a decoding function which will be used by Bob, okay, which maps an output of the channel to a message. Okay, so it could be even randomized, so in the sense that given I, the way I encode it is probabilistic. Okay, so the probability that I is encoded in x, and same thing for the decoder. Okay, the decoder can be randomized as well. Okay, so this is what I want to find. I want to find this E and D, such that, of course, the success probability, which is the success condition here, that the output of Bob, which I call J here, is equal to I with the largest possible probability. Okay, so again, let's rewrite this mathematically. So yeah, again, E and D are my variables now, and W is something fixed. I see it as the input to my problem. Okay, and what is the optimal success probability I can achieve for sending k messages using a noisy channel W? It's given by this following program. Okay, so I maximize, these are my variables, E and D are my variables. And remember, what I want is for a given E and D, I can compute the success probability. How do I do that? Okay, so I sum over all possible messages I take the average. So an assumption I didn't make explicit yet, so is that I will assume that I have a uniform distribution over all possible messages. Okay, so I look at the average success probability over the choice of the messages of the following quantity. So here, this is the probability that I is mapped to x by the encoder, and then this is the probability that the noisy channel maps x to y, and then the decoder maps y to the same I that was encoded. Okay, so this is the success probability. And of course, what are the set of valid encoders and decoders? It's very simple to write. There should be a valid probability distribution. So for every I, if I sum over x, then I should get 1, and similarly for the decoder. Okay, so it should be a valid encoding and decoding. Okay, so this is the central quantity I'm interested in, and perhaps the central result in this area of channel coding is Shannon's theorem, which sure most of you are familiar with, but let me just restate it in this language. Okay, so here is a setting where I look at a particular class of noisy channels, so namely the ones that are obtained by taking a base, think of it as a small noisy channel W, okay, and then I repeat it n times independently. Okay, so this is what I wrote here, so W here. Okay, and I look at this as a big channel, and what I would like to do is to try to determine this, remember this notation, P success of Wn, okay, for some values of k, and it turns out that in this case we have a very good characterization of this optimal success probability that I can reach. Okay, so namely it's as follows. So for this base small channel, I can compute this quantity. So this entropic quantity, it's a maximization over the input probability distribution of the mutual information between the input and the output. Okay, so this is a simple convex optimization over this small channel, one copy of the channel. And then we have this very nice threshold behavior, which says that if the number of messages I try to send is smaller than 2 to this quantity, this capacity, okay, then the success probability goes to 1. Okay, but if I try to send more than this number of messages, k is strictly bigger than 2 to the capacity, then the success probability goes to 0. Okay, yeah, so technically this was not proven by Shannon. This is what we call strong converse, but okay, spirit. It was proven a bit later. Okay, so yeah, so yes, question, yeah. Uh-huh. But so what do you mean exactly? So you yes, in parallel. Yes. Mhm. So I think what you mean is because these two people are in different places, right? So Alice and Bob are in different places. So do you mean that there is feedback? Yeah. Okay, so this is a very good question. Yes, you can study these questions when there is feedback from the receiver to the sender, and you can, of course, it's a natural question, and it can be studied, and yeah, this is very well studied. But okay, so here I'm focusing on the basic setting. With no feedback. Yeah. Okay, so yeah, the only way to communicate between Alice and Bob either way is through the channel. Okay, so yeah, this is the traditional Shannon theory type setting, and so this is typical. So then, of course, people in information theory, we study different kinds of settings, not just the channel coding, but for example, channel coding with feedback, source coding, the settings where we have multiple senders, multiple receivers, and we try to come up with statements like this. Sometimes it works like in this setting, sometimes it doesn't work so well. Okay, so here, as I said, I want to take a slightly different approach, and I want to see this more as a computational problem. So suppose now W is completely general, so it's a completely general channel. It doesn't necessarily have the structure of IID. Okay, and I take this K, which is the number of messages I want to send. Okay. And I see this as the input of a computational problem, and I would like an efficient algorithm to compute this optimal success probability. Okay, so I think, yeah, this has several motivations. So I think it's a very natural question, but so let me give some more concrete motivations. So first is the generality. So in the sense that if you're interested in a channel which is not necessarily IID, but a bit more general, then Shannon's theorem does not necessarily give you the answer. Also, the asymptotic, I mean, the fact that Shannon's theorem is asymptotic in the sense that you have to take n going to infinity, then this you might have an IID channel, but you have a very small number of uses, for example, and you might want to understand what is the optimal success probability I can have. Okay. Perhaps more importantly, for me at least, is that in the quantum case, now if the channel is a noisy quantum channel, even in this IID scenario, asymptotic scenario, everything, we don't have a satisfactory version. I mean, we have some versions of this, but to my opinion, it's not satisfactory. And I'll say a bit more about it later. Okay, so I think that's why I think this relaxed view, where instead of trying to characterize exactly the rate at which you can code with some closed form entropic expression, is maybe a bit too much to ask, and we can instead ask to have just an algorithm that computes the optimal success probabilities. Okay, so that's it for the motivation. So now I'll try to we'll study in a bit more detail the classical case, and yeah, see that we can characterize quite tightly the complexity of this problem. Okay, so here I've just rewritten the central optimization program that we're interested in here. Okay, so it's so yeah, you see, so remember E and D are the variables, so the constraints are linear and nice, but the objective function you see is not linear in E and D. It's quadratic, so, or it's bilinear more precisely. Yeah, I didn't put them again, but yes, thanks. Yeah, E and D are positive. Okay, so yeah, so for this case, it's possible to rewrite it with some simple manipulations to make it look more like a combinatorial optimization program. Okay, so this is relatively easy. So it's relatively easy to see that you may assume that there is an optimal solution, E and D, such that these numbers, E and D, are 0 or 1. Okay, okay, so in this setting, then the set of x's such that there is an I that maps to x. You can call this the code. This is what we usually call the code in information theory. This is just the set of inputs to the channel that are used by the person who wants to send the messages. Okay, so that's why I'm calling it C. Okay, and then the structure of this decoder is also simple in the sense that for a given y, so for an output of the channel, you map it to the message I, which maximizes W of y given xi. It's also called the maximum likelihood decoder. Okay, so by putting all of these things together, you can rewrite the success probability in this form. So okay, so now it's an optimization over all the possible subsets of inputs to the channel. So C is a subset of X, and the size of C is just the number of messages you would like to send. Right? For each message, you have a code word. And then you optimize this function fw of c. So this is a function on subsets. And it's written as follows. So f of c is just the sum over all possible outputs to the channel of the maximum, so the element in the code that maximizes w of y given x. Okay, so again, this is relatively easy, just rewriting using these basic facts. Okay, so this is nice. So now at least this gives a finite algorithm to solve this. What could I do? I could just loop over all possible codes, C, and find the one which maximizes this quantity. But of course, you see that this is not very satisfactory because the number of subsets is like if I call size of x n, then it's the number of set C is n choose k. Okay, so this is not satisfactory. I want something more efficient than this. Okay, so then just trying all the possible C's. Okay, so there's a natural heuristic you can think of in this setting, is instead of looping over all possible codes of size k, you could do the following. You just construct the set C in a greedy fashion. Okay, so you start with an empty set, okay, and then you just add the code word or the element of the input x, which increases your objective function by the most. Okay, so this is a function on subsets. So you start with the empty set. For the empty sets, it's 0. And then you add the element which maximizes fw of c. Okay, and then you add the elements one by one. So you add the first element. Okay, you add the element which adds the most, and then for I equals 2, you add the second element, etc. So you see, of course, this is much more efficient because once you put a guy in the code, you don't come back over this decision. Okay, so that's why it's called greedy, right? It's you do greedy choices, okay, and then of course you return C. Okay, so it's not clear at all whether this is a priori it will not be optimal. This, Okay, and the question we would like to ask is this relatively simple heuristic, how close is it to the optimal? Okay, so I've just rewritten this. And so for that, we can make a very simple observation that this function f has some very simple properties which will show actually that the greedy algorithm is not that bad. Okay, so what are these properties? So first, fw is monotone, so this is obvious, right? If you make c larger, then fw is larger. Okay, and the important property is that it's something called submodular. Okay, so like one way of seeing this is that it has the property of diminishing returns. So if I consider two sets, C and C prime, so C is included in C prime, then it has the property that if I add any element x to C, the increase that I get is bigger than the increase I would have gotten for the larger set C prime. Okay, so that's why it's called diminishing returns, because the return I get from adding x is more on the smaller sets. Okay, and here there is a very standard result in combinatorial optimization from the 70s that says that this greedy algorithm I presented, if you apply it for a function which is monotone and submodular, and actually non-negative, but here it's non-negative, then it cannot be too far from the optimal in this following sense, with this factor 1 minus 1 over e. Okay. So this is like 0.63 something. Okay, so the greedy algorithm can return a code which is suboptimal, but the success probability it achieves will not differ from the optimal by, will differ by only a factor of 1 minus 1 over e at most. Okay, so the direct corollary of this is that this greedy algorithm can return a code, C, in time which is very reasonable, so the size of the representation of the channel times the number of messages in such a way. So remember there was 1 over k in front of the, yeah, actually it's here. Yeah, so there is a 1 over k. Okay, so the same 1 over k here. So it will return something which is, of course, it's at most the success probability of the optimal, but it's at least also 1 minus 1 over e times the optimal success probability. Okay, so that's already good. I can construct the code in an efficient way, which is not too far from optimal. So this is nice. Okay, so now we can start asking, is this 1 minus 1 over e something special, or can we improve it to get something even closer to 1? Okay, and it turns out that no, we cannot do that. Okay, let me maybe check how am I doing on time. Where's my phone? Okay, I'm fine, I think. Okay, so yeah, so it turns out that you cannot do better than this 1 minus 1 over e approximation ratio, and the reason is the following. Okay, so there is a famous theorem in the area of hardness of approximation, which says the following, that there is this famous problem called the maximum coverage problem. Okay, and there is a famous result which says that there is no polynomial time algorithm that achieves an approximation ratio which is better than 1 minus 1 over e, okay, unless p is equal to np. Okay, so if you find an approximation algorithm which achieves a ratio which is slightly better than 1 minus 1 over e, then you have proven that p is equal to np. Okay. Okay, so this is based on this maximum coverage problem. Maybe, yeah, it doesn't matter so much what this problem is, but there is a very simple reduction to this problem we were considering of finding the optimal success probability. Okay, so yeah, so a direct corollary of this is that we cannot achieve an approximation ratio which is better than 1 minus 1 over e for this problem of interest of finding the optimal channel code. Yes? Yeah, of course, of course. This is standard complexity. Yeah. So no, I don't know for this setting, but yeah, the thing is, average complexity is a bit hard to. So you have to put a distribution on inputs, right? So what distribution do you choose? So yeah, no, I don't know of average case results for this problem. Okay, so let's now move on. So you see this greedy algorithm, what it gives you is lower bound on this optimal success probability, but because it gives you a code which achieves some success probability, so it gives you lower bounds. It gives you possibility results. So now suppose I'm interested in impossibility results, saying that you cannot achieve a success probability higher than something. Okay, so yeah, this is called converse in information theory. Suppose I want to find upper bounds on this optimal success probabilities. Okay, so here, actually the motivation that, I mean, when I studied this problem, I came from a slightly different motivation, which is to try to look at the setting of channel coding that I presented before, but now you suppose that the sender and the receiver, they share entanglement. Okay? Yeah, so I won't talk too much about the setting because Mario will talk more about it later. But yeah, so this is the setting where Alice and Bob, they have some pre-shared entanglement which they can use in order to improve the success probability. Okay, so yeah, they have the state and they have measurements. Okay, and yeah, so you can ask now if with this entanglement between the encoder and the decoder, so I can define this quantum success probability, and of course this is larger than the success probability without any assistant, without any entanglement between the sender and the receiver. But the question is, can it be much higher? So we have examples where it's a bit higher, but so my motivation for studying this question was, can this be arbitrarily higher than the setting without entanglement? Okay, so okay, so now let's get back to, and we'll see, we'll solve this question on the way. But now what I want to do is find an upper bound on this optimal success probability. Okay, so the natural thing to do is to look at this problem, right, and consider linear programming relaxation of it. Okay, so you see this is an optimization over subsets of X. You can naturally relax it to a linear program by introducing these variables. Okay, so yeah, so maybe the most important is this one, this variable px. So this px, think of it as a fractional code. So in this setting, think of px as equal to 1 if x is in my code and 0 otherwise. Okay, so this is my px. But now I relax it and I allow these px's to just be arbitrary real numbers between 0 and 1. Okay, so this is a relaxation, so it will give something which is potentially larger. Okay, so yeah, and rxy is just a variable which is used to take into account exactly this maximum. Okay, so instead, I mean, we just replace this maximum by an averaging with this rxy, and this is how you write it. Okay, so it's a standard way of writing a linear programming relaxation where we replace this, think of it as the integral subset of x into a fractional subset with these px's. Okay, so as I said, it's quite clear that the optimal success probability is of the original problem is upper bounded by the value of this LP, right? Because it suffices to take a specific solution where you take the px's to be 0 or 1. Okay, then it's easy to check that you get a valid feasible solution. Okay, but it might be that this LP is larger, strictly larger. Okay, and with a little bit of work, you can even show that this quantum success probability that I presented here, even though not in much detail, it's possible to show that even with entanglement, this is still a lower bound on this LP. Okay. Yeah, so in other words, given a quantum strategy, you can construct a feasible solution for this LP. Okay, so okay, so why is this interesting? Is because now if I can show that this this LP is not too far from the optimal success probability, then it will show, because this quantum success probability is sandwiched in between, that there's no big difference. Okay, so actually it turns out that this LP corresponds to the optimal success probability using a non-signaling box between the sender and the receiver. Okay, I won't get into details of what this means, but there is a natural interpretation to this LP also, operational interpretation. And it actually corresponds to something which is well studied in the information theory literature, which is sometimes called the PPV bound or meta-converse, due to Polyansky, Poor, and Verdun. Okay. Okay, so let me recap a bit and then state the result. Okay, so remember we have this, the central quantity we're interested in is this one. This is the optimal success probability for a given channel and number of messages. Okay, I'm also interested in this version where I have some quantum helper, okay, with entanglement. Okay, and now these are sandwiched with, on the two sides by some efficiently computable quantities. So namely what I get using the greedy algorithm. Okay, so the greedy algorithm on W and K, I get this quantity, which is smaller than all of them. And now this LP, which is also efficiently computable, and it's bigger than all of these. Okay. And what we've seen a couple of slides ago is that between here and here, there's not too much difference. Okay, there is a at most constant factor. Okay. And now, okay, so now here, the main result is that actually there is not a big difference between these two efficient things. So between the greedy algorithm and the LP relaxation, they cannot be further than a factor of 1 minus 1 over E. Okay. Okay, so yeah, think of K is equal to L for now. Okay. So yeah, if K is equal to L, this is just 1 minus 1 over E, and this is the ratio between the greedy and the LP. Okay, so it turns out that okay, yeah, you can say that this 0.63 is not very good. So suppose that I get, suppose for example, for some reason I know the value of this LP, that it gives 1, for example. Then what this says is that I know that there is a code, and this code will be returned by the greedy algorithm that will return a success probability of 0.63. Okay, but you can say, okay, success probability of 0.63 is not very satisfactory. I want like 0.99 success probability. Okay, so it turns out you can get that, but at the cost of sending slightly less messages. Okay, so what this is saying is, suppose that the LP tells you that to send a certain number of messages, K, I get a success probability of 1. Then this will tell you that the greedy, if you ask it not to send K possible messages, but 6 bits less, okay, so if I divide this by 2 to the 6, then I will get a success probability of 0.99. Okay, so this is a bit more general, the result. This is what I want to say. Yes? Yeah. So so K and L are both number of messages that I want to send. Okay? So yeah, first of all, think of L is equal to K first. This is comparing what the LP gives for sending K messages over W and what the greedy gives for sending K messages over W. Okay, so now suppose I want you see. Suppose I want to, yeah. So because there are two parameters, the success probability and the number of messages. So at the cost of reducing a bit the number of messages, I can increase this ratio. That's what I wanted to say. Okay, so yeah, a couple of comments on applications of this or implications is that. If you allow entanglement between sender and receiver, this is saying that you gain at most a factor of 1 minus 1 over E over the setting where you don't use any entanglement. Okay, because remember this PQ success is sandwiched in between these two. Okay, and also, yeah, it shows also that this PPV bound, which was used a lot, and it had enormous success. This is perhaps one reason, is that it's actually quite tight in this sense. And actually, you can come up with channels where this ratio is achieved, so this relation is optimal. Okay, so yeah, I won't say much on the proof of this, but maybe one word on it. It's maybe not very informative, but yeah, so the way you analyze this is that you look at the similar analysis of the greedy algorithm, and instead of, usually you compare it to the optimal. So you start with the optimal, and you say the optimal has some properties, and that allow you to relate to the greedy. Now you start with the LP itself, and you generalize the proof in such a way that you're related to the LP. Okay, we have also another proof, an alternative proof, which actually doesn't give something as strong, which it only relates the LP to this quantity, which is more standard, which is it is done by randomized rounding. So you take the LP, it's fractional, you interpret it as probabilities, you come up with the code as a function of these probabilities, and you analyze in expectation how well it does. Okay, so let me just summarize this classical part. So we saw that we got relatively tight, efficient upper bounds and lower bounds on the optimal success probability I can achieve for sending classical information over classical channels with approximation guarantees, which are basically optimal. Okay, so now, yes. Ah, sorry. Yeah. Yes. Yes. I mean, it's not always that SDPs perform better. So yeah. So yeah, this result. I mean, So yeah. So you're right. So yeah. So you can definitely come up with an SDP relaxation, definitely. And yeah, it might be, but you're right. So, okay, it might be better on specific channels. And actually, Mario will talk about this. So yeah, it might be better for some specific channels. But like there will always be, even if you come with a complicated SDP relaxation, okay, except if it's large, but a reasonable SDP relaxation, then either you would have solved the P versus NP, or there will be an instance where it will fail. Yes. So it's slightly different from parallel repetition, but so okay, maybe I'll let you continue the question. Yes. So are you talking about the quantum value? Yes. Yeah. Oh, no. I don't know of an instance, but this is. So I know of instances where the classical value is. Okay, I don't remember the value exactly, but let's say 0.7, and the quantum value is 0.8. So but it never reaches this 1 minus 1 over e thing. And actually, yeah. So one open question, we don't know. So I don't know, at least of. So okay, so it turns out that this factor 1 minus 1 over e is optimal if you compare the classical value and the non-signaling value. So there are games that achieve this ratio, but it's basically related to the fact that this factor cannot be improved, and the fact that this is really the non-signaling value. But for the quantum value, I mean, we have channels, or you can think of it as games if you want, where there is a difference, but we don't know. I mean, I don't remember the largest ratio we can get, but maybe it's 0.8 or something like this, whereas this is 0.63. So I don't know. Does this reply to your question, or? Mm-hmm. 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 Yes. Okay. I see what you mean. Okay, so the thing is, okay. So these are special kinds of games, but they're so if you repeat the game, it doesn't give you. So okay, let's call these kinds of games channel games. Okay, if you start with a channel game and you parallel repeat it, it's not necessarily a channel game. You see? Okay, yeah, but it's a fact. I'm just saying it as a fact, and then yeah, you can yeah, okay, yeah, exactly. It's not necessary. Yeah, yeah. Okay. Actually, there is something here. Okay, so any other questions? Because yeah, this is in between the classical and the other questions about the classical. Okay, so now I'll talk about now the quantum counterpart of this. So there are many possible quantum counterparts you can come up with, but so here I'll be considered I'll consider probably the most natural one, which is that the channel itself is quantum. Okay, so from A to B, so a quantum channel is a completely positive mathematically. It's a completely positive trace preserving map from the set of linear operators on A to the set of linear operators on B. Okay, and my objective now is to communicate some quantum information. So I want to take a state psi in C to the power k. So I want to send a k-dimensional object to. So Alice wants to send the k-dimensional quantum state to Bob. Okay, so you see it's similar than before. So our task is to design a system which maximizes the transmission fidelity. Okay, so let's model it a bit more precisely here. So what will be an encoder here will be again a valid quantum channel. So it's a completely positive trace preserving map E. Okay, and the decoder similarly. Okay, and so the way I'm gonna model the sending of quantum information. I mean, we know that sending quantum information is the same as being able to recover a maximally entangled pair. So I'll do that. So phi k here is a maximally entangled state, okay, of dimension k. Okay, so I keep this part as a reference, and I put this into the encoder. It goes through the noisy channel. It goes through the decoder. I get a state sigma here, which might be mixed, and my objective is to maximize the fidelity between sigma and this maximally entangled state phi k. Okay, so so I write it this way. So I maximize the okay, so written in a bit more detail here is what happens. So I input phi k to, I mean, I keep the reference as is, and to the other side I apply EWD, okay, and then I sandwich this with the maximally entangled state, okay. So, and subject to now my constraints, remember these, instead of just having the sums being 1, so now I have that E and D are valid quantum channels. Completely positive trace preserving maps. Okay, so now, okay, before getting into this computational approach, let's see what is known in this standard Shannon theoretic language. Okay, so so here I look at a base channel W, and then I take n independent copies of it. Okay, so here it turns out there is a kind of Shannon theorem. However, yeah, okay, so let me state what it is. So you can define a quantity which is called the coherent information. It's think of it as an analog of a mutual information a bit. It's not a mutual information, but it plays the role here, this role. So it's some quantity, it doesn't matter what the details are. And now it turns out you also have a kind of threshold behavior, even though, okay, we don't know if above the capacity, we just know it does not converge to 1. But now the capacity is not given by the simple formula IC of W. It's given by this regularized formula where you have to take the limit when n goes to infinity of 1 over n times this quantity evaluated on W tensor n. Okay, so yeah, so this means that in general we don't know how to compute it. So okay, for some special channels we know that actually you don't need this limit. So in the sense that this is equal to IC of W. So this quantity is actually additive. In some cases this happens, but in many cases it doesn't happen. So in particular, it's known that it doesn't happen for perhaps one of the simplest channels, like the analog of the binary symmetric channel, which is qubit depolarizing channel. Okay, so your input is a qubit. With probability 1 minus p, you keep exactly the same state, and with probability p, you just return a maximally mixed state. Okay, so this capacity is unknown for this channel. In particular, it's not known when it starts being 0. Okay, so yeah. So as I said again, my objective here is to okay. I'll take a different perspective, and W and K are inputs, and I want to just compute F of WK. Okay, so to write this, okay, to write this a bit more precisely, we have to choose a representation for the quantum channels. There are many ways of representing a channel. It turns out, the simplest way here to use is this Choi-Jamilkowski representation for a channel, okay, which is obtained by just applying the channel to the to a maximum entangled state. And okay, by just rewriting, you get an expression of this form. Okay, let me go a bit through it. So, okay, so now you remember we were optimizing over encoders and decoders. So this now what plays the role of an encoder is this positive semi-definite operator, so which acts on two systems. One which I call K because it's of dimension K, and one which I call A. Okay, so it's a bipartite state. Think of it as a bipartite state on a system of dimension K and on A. So remember, A is the inputs of the channel. Okay, so this should be positive semi-definite, but it should be a valid choice state, right? So it should have that when I take the partial trace over A, then I should get something which is maximally mixed. Okay, similarly for D, it's also a positive semi-definite operator with some constraint that dB is equal to identity over the dimension. Okay, and what I'm optimizing now is okay, the trace of the product of two operators. So this operator is a fixed operator. So this is the choice state of the map of the channel, and this is the maximally entangled state. Okay, so this is constant. But now what I'm optimizing over is these two things, E and D. Okay, and you see that here so E acts on KA and D on K bar B, and here it's on KK bar and AB. So it doesn't simplify. Okay, so this is the program. So you see first, okay, so similarly to the classical case, it's also bilinear. So if I fix E, then and I optimize over D, this is just a semi-definite program. Okay. Similarly, if I fix D and I optimize over E, it's also a semi-definite program. Okay. So actually, this observation was made a long time ago by this paper Reimpel, Werner, and Fletcher, Shore, and Wynn. And they suggested this algorithm, which is to basically to do alternating optimization. So to start with some, let's say, random E, and then optimize over D, and then take the optimal D, and then optimize again over E, etc. Okay. Okay. So this is a nice algorithm, but so yeah, it seems hard to analyze, and there's no convergence guarantee. So what we'll try to do here is something. It's related, but it's to rather find a family of converging hierarchy of semi-definite programs for this F of WK. Okay, so let me just rewrite this a little bit, okay, so that it looks maybe a bit more familiar. Okay, so this is just the same thing, F of WK. So I can just rewrite this as, okay, so maybe I first notice something is that okay, so let me do it this way. So it's equal to the maximization over all possible x's that are of this form, ek tensor d k bar b. Okay, so x and c of trace of xm, right? But then, of course, because this is linear, then I can add the convex hull here. Okay, so I can optimize over the convex hull of all such states. By the way, M is just this matrix that was there before, but okay, just M for short. Okay, so this convex set T might remind you of a very well-studied convex set in the quantum information, which is the set of separable states, right? Which is just the convex hull of the positive semi-definite operators E and D, okay, each of trace 1. Okay, so yeah, so this set SEP is very well studied and well known that it can be approximated with the set of so-called extendable states. So maybe I'll take the next slide to talk a bit about extendable states. I'm not sure everyone knows about it, so I'll remind you of this extendability. Okay, so now let's forget a bit the problem of channels and now consider the set of just separable states and try to approximate this convex set with some easy sets. Okay, so yeah, so as I said, the set of separable states. So now between two systems, which I call X and Y. Okay, so it's just the convex hull of the products EX tensor dy that are of this form. Okay, so okay, so there are many ways of approximating the set, but perhaps one nice way of doing it is using these symmetric extensions, okay, which was in this paper, but I mean it has origins a bit before, which is the following. Okay, so which starts from the following observation: is that start with some separable states omega xy. Okay, so by definition you can write it as follows, as a sum over I of pi exi dyi. Okay, just by definition. Okay, so now I can construct an extension of this state omega where I have multiple y sets. Okay, so I don't have just one y, I have multiple of them. So I have rho x y1 to yt. Okay, where I just, so I have ex tensor dy1, tensor dy2, tensor dyt. Okay, and now you observe that this part, the different y's, is symmetric in the sense that if I permute these different systems, I get exactly the same state. Okay, so this motivates the definition of the set, so the set of extendable states, which is the set of omega xy, such that there is an extension that is invariant under permuting these y systems. Okay, and that of course gives omega. Okay, so you see this is an SDP representable set, so it's a nice set, you can optimize over it. Okay, and it's a larger set than the set of separable states. Okay. Okay, so and as you increase t, so this t is a parameter, as you increase it, you of course get smaller and smaller sets. And it's possible to show, it's non-trivial, but it's possible to show that the set of extendable states, infinitely extendable states, coincides exactly with the set of separable states. Okay. Yeah, so this is nice, but it would be nice to have a more quantitative statement where it says how large should I take t for this approximation to be good. Okay, and so for that you can use the finite quantum de Finetti theorem, which will allow you to do that, which says the following, which says that if you take a state which is t extendable, then it means there is a separable state, okay, which is close to my original state. This is the trace norm, by the way. And how close is given by this formula. So 2d dimension of y squared over t. So if you take t sufficiently larger than 2 times dimension of y squared, then you get a good bound. Actually, this is what you would want usually, because so what you would do to approximate is, okay, so you cannot test whether your state is separable or not, but you can test whether your state is extendable. So imagine you have omega xy, you know it's extendable, okay? So it doesn't mean that it's separable, okay? But this tells you that it's at least, it might not be separable, but there is a separable state which is epsilon closed. So it's in the good direction. Yeah, it's infinitely extendable. Yeah. Okay, so okay, so oops, sorry. yeah, here. Okay, so now let's get back to our problem. So remember, we were not quite interested in the set of all separable states, but rather in some set of this form with some more restrictions. So we don't take the set of all convex products, but rather we put these extra linear conditions. Okay, so so there is a natural construction you can come up with, which is similar. So, but let me just, for the purpose of this talk, to simplify the notation, I will not consider these two constraints. I'll just consider one of them. So one of them, I just put that the trace is equal to 1, just normalize. But the other, I leave the constraint that the marginal is identity. Okay, this is just, otherwise the notation will be very hard to read. I mean, it's already not so easy, but okay, so now I want to approximate this set. So okay, which you can see it as the set of separable states, except that I put linear conditions on the elements of which it can be a convex combination of. Okay, so okay, so I use the same idea. So I start with a state omega, which is in this set C prime. So I can write it in this way. Okay, so let's extend it in a symmetric way similarly. So I extend it in this way. So it's still invariant under permuting these systems. Okay, but now I need to enforce this linear condition, right? I need to enforce it in some way. And so one simple way of enforcing it is as follows. So I agree it's not so easy to read, but so okay, so here what did I do? So I have a state on all of these systems. So I extended the k bar and the b's. Okay, and now I took the partial trace over k bar t only. Okay, so I removed, so this system which was supposed to be k bar t, I removed it. I took the partial trace over it. Okay, but here we know that if I take the partial trace over k bar here, then I get identity here. Okay, and then the rest is just rho on k1 bar t, b1, etc. until t minus 1. Okay, so I have this linear condition. Okay, so I can just add this to my extendability condition. So I want a state rho, which is an extension of omega, which is permutation invariant, but also which has this property that if I take the partial trace over the last k bar t, then I get tensor identity. Okay, so again, this is an SDP representable set. Okay, so the thing is, but it's not clear whether this converges to C prime. So whether when I take t larger, that this goes to C prime. Okay, so that's why so the final quantum definity is not directly applicable. So that's why I'm saying we need a definity that takes into account linear constraints. Okay, so this is what we can show here. So again, abstract away from the channel coding picture, and let's just try to think of a definity where we put linear conditions. Okay, linear constraints. Okay, let me do that quickly. Okay, so yeah, so what does a definity theorem typically say? So it says that you start with a state rho, which is permutation invariant. Okay, so rho A so I only take multiple copies of B. Okay, so it's permutation invariant for the B systems. Okay, and suppose now I have this linear condition. So namely that if I act with some linear map on BT, then it maps me to the state rho with B1 to BT minus 1 tensor some QC. Okay. So what does this say here? It says that I can approximate the state rho AB, okay, which is just the first marginal here, rho AB, by a state which is a convex combination, okay, of product states. But not only that, each element of this convex combination satisfies the linear constraint. Okay, that gamma, if I apply it to this psi b of psi, I always get QC. Okay. So this is, remember, the usual term from De Finetti, and we get something extra, which is a bit worse. Yes? Yeah, it doesn't. Yeah. Yes, yes. So okay, maybe I'll skip the proof idea maybe, and then I can say that an interesting special case is a de Finetti for quantum channels. So if the linear constraints are the constraints that come from the choice state, then you get de Finetti for quantum channels. Okay, the infinite version was before, and okay, let me skip that. Let me maybe conclude quickly. Yeah, so again, the problem of, we saw the problem of reliable transmission over a noisy channel from an algorithmic point of view. And in the classical case, we give good upper bounds and lower bounds, and that were basically tight. Okay, in the quantum setting, much less is known. So we gave a hierarchy of upper approximations, okay, using SDPs. And we can prove finite convergence bound using this constrained de Finetti theorem. Okay, but of course, if you want to use this in practice, these bounds are only reasonable for very small dimensions. Okay, because if you put in everything together, you'll get an extendability which is quite large. Okay, so of course there are many open problems in this area, like getting better algorithm guarantees or hardness results in the quantum setting. Almost everything is open. And let me mention something is that, okay, here I consider the very general question of you take a general channel, okay, but you might be interested in channel with a specific structure. And in this case, you would be interested in more efficient algorithms that use these symmetries. Okay, I'll stop here. Thank you.